All right, hello, this is Mr. Myers here with Chem 2 7th Hour. We're going to go through live and see how it goes, the Chem 2 solutions review for tomorrow's test, for those of you that are not here. And so I've got the webcam set up. Get this a little bit bigger here. And so we'll start off looking at the review page. We've got at the top here solubility. And so there's a variety of components that are going to be involved. Before we get to some of this information on solubility, one thing I want to alert you to is that we need to be able to discuss the difference between dissolving and dissociating. Understanding that dissolve is what happens when covalent or molecular compounds separate from each other in solvent and become solvated. So they separate from each other, separate from other molecules. On the other hand, when things dissociate, these are ionic compounds. And ionic compounds, during solvation, the ions come apart or break apart from each other. So come apart from one another and are surrounded by solvent molecules, typically water if the solvent is water. Okay, so that's a very basic difference, definition between dissolve and dissociate. The primary part is knowing that dissolve is with covalent molecular compounds, while dissociate is for ionic compounds. Further understanding that the ions actually separate from one another and come apart and break apart, whereas the covalent compounds, when they dissolve, the individual atoms do not break apart from each other. So we still have our compound that is bonded together, but all of the individual molecules separate from each other. So you have all these different molecules surrounded by water. One place that I would suggest you go to for this is go to our Google site and wait for it to load. And then go to my chemistry videos tab. And from there, under chemistry 2 in unit 2, we have what happens when stuff dissolves. If you go to this video on YouTube, I won't play it, but Tyler DeWitt has a series of videos, over 155,000 subscribers, so he knows his stuff. The video on here, he actually works through the modeling of what goes on between dissolve and dissociate. We've watched it in class, and so I'd suggest to go back and take a look at this one for further understanding. Back to the review. All right, so let's look further then at the review page itself. We have questions about solubility here. And so given the following information, be able to draw a solubility curve and answer the following questions. On the test tomorrow, I won't have you draw a solubility curve. I'll have one provided for you, and you'll still have to analyze it and answer questions based upon that data. Okay, so this one, thanks to Sean, who provided his review sheet here for me, we have the temperature versus the solubility. And we see as the temperature increases, it appears the solubility also increases, which is true for things that are solid solutes. So when we take a solid solute, solvate it within water, our solvent, we should see that as temperature goes up, so does the solubility, meaning more of the salt can mix or be solvated within the solution. So in A, what is the general relationship between solubility and temperature? So put solubility here. So A, solubility and temperature, the general relationship is that as temperature goes up, so does solubility. Understanding that this is for solids, okay, or solid solutes. And B, is the solute likely to be a solid or a gas, and why? Well, based upon the data that we have here, we see a direct relationship between solubility and temperature. And so we'd say in B, it's likely a solid solute because it has that relationship, okay? Which means that for gases, it's an inverse relationship. So as the temperature increases for gases, the solubility actually goes down. Okay, so do be aware of that relationship. For C, what is the solubility at 45 degrees Celsius? We look on Sean's graph here, which 45 is about here. And so we bring it up, and it looks like it's going to be around maybe 4.2 grams, 4.25 grams. Really what I would suggest is to utilize the entire graph, so maybe make a different scale. And by doing that, we can expand the graph and what we're looking at and read it much more clearly. Okay. D, to what temperature would you have to heat it to get 4.75 grams to dissolve? So we look for 4 grams here and 5, so 4.75 is about here. And as we come across and down, it looks like that is at about what he marked to be 54 degrees Celsius. Okay. Anyone got something different? 52? I'd say that's close enough. Really, it depends on how you graphed it. And on the test tomorrow, you'll have a graph provided, so you'll be doing it based upon that graph. Okay. In E, why do we say the curve represents the saturation point for the solution at a given temperature? When we say that, we're saying that at that temperature, we have dissolved the most amount of solute possible, and anything else that we add just floats, or not floats, but sinks to the bottom. Okay, so what does it represent the saturation point? So for saturation point, we say that we've reached the maximum amount of solute that can be solvated at that temperature. Okay. Any questions so far? All right, let's go on ahead then to colligative properties. Okay, we touched on colligative properties Thursday when we were in the lab. Okay, recall that with colligative properties, it's not so much what we have in the solution that affects things, but rather how much of it, and more of the quantity and how much that substance might break down. Okay, so with colligative properties with A is asking what happens to the boiling point right here and freezing point of water when a solute is added to it. So we say for A, I'm going to bring this up back to the top here. So for A, what happens to boiling point? What do we call it for boiling point? Elevation or depression? Elevation. So what does that mean for boiling point? What's happening to it? It increases. So boiling point is going to increase, right? We call that an elevation. And so what's going on there is as a solute is added, we're looking at the kind of the intermolecular forces within water that for them to overcome or have enough energy to change phases from liquid to gas, that has to be greater than the forces and attractions between water and the particles themselves. Okay. So as a solute is added, water molecules solvate with solute particles. Okay, so solute is added, H2O solvates with solute particles. We need more energy to overcome these forces between water and solute. In order to vaporize or boil. Okay, because for boiling point, when we go to boil, we're saying that we're going through a phase change of vaporization. In other words, we have to have enough energy to overcome the forces that are keeping the liquid particles together. And usually for water, we reach enough energy to do that phase change at 100 degrees Celsius. Okay, but when we add a solute to the mix, well, now the water is competing with the solute, and so the water wants to solvate it and surround it. So now we've got to break apart that attraction between the water and the solute and have enough energy to overcome those in order to then get to the boiling point. And so what that does then is it increases that boiling point significantly. Okay. For example, if we put sodium chloride in water and we go to boil it, if any of you guys go to boil water to make pasta, the salt makes the water take longer to boil because we've increased that boiling point. But once we're at a higher temperature, the pasta is able to cook much faster because it's cooking at a higher temperature. So there's a trade-off. Take longer to boil, cook the pasta quicker. Okay, decision's up to you. For freezing point, we call that freezing point depression. And so kind of similar to boiling point, when we add the solute, the water wants, yeah. Oops. Thank you. The water wants to solvate the salt particles rather than come closer together. And so there's going to be that competing factor. And so again, we see with freezing point that the freezing point is going to go down. We call it a depression. Okay. And we have more on that in the notes. So I gave you guys a set of slides that you guys can take a look at. For B, how does density of solution change when a solute is added to it? We should see that density increases with the addition of solute. Remember that density is mass over volume. And in this case, the volume of our solution should stay about the same, but we add more solute to it. We're adding more of a ionic salt, let's say. And so we have increased mass, the volume stays the same, so the density is going to go up. And then in part C, which would affect the boiling point more, NaCl or calcium bromide? Remember, with colligative properties, we look for number of parts the compound breaks into. Okay. My definition here is not as eloquent as what it was in class last week, but essentially we look to see NaCl, how many ions would that break apart into? 2. So 2 parts versus calcium bromide, how many ions would break apart there? How many? 3. You did. 3. We have 1 calcium, 2 bromide, so it'd be 3 parts that it would break into. So the more parts that you can break into, the increased effect that colligative property will have. Okay, so that would be like on the roads, I'd rather use, or on my driveway, perhaps calcium chloride to melt the ice and keep it melted, or to keep the water from freezing, versus NaCl. In one part, calcium chloride might be better environmentally, but also it breaks into more parts, more ions, and so the depression of the freezing point is going to be much greater. Okay. All right, let's flip the page and we will go to molarity. Yeah.
So,
Calcium bromide. Yeah. So the more parts that it breaks into, then it's going to have the greater effect, whether it's freezing point or boiling point that we're looking at. Do keep in mind for that one though, if you have something like sugar, let's say glucose, C6H12O6, there's a lot more atoms there, but it's a covalent compound, so it's not going to break down into individual atoms. So glucose would effectively be one part. Okay. Whereas like NaCl would be two parts because it's ionic. We can break it into sodium ion, chloride ion, and then calcium bromide could be calcium ion and two bromide ions. Does that make sense? Okay. So I always look first to see, am I dealing with ionic, meaning does it have a metal as the cation, or am I dealing with something made up of all non-metals, which would be covalent? The covalents, even if they have 20 atoms that make up the compound, it's still one unit. All right. So starting to look here at molarity. All right. So for molarity, remember that molarity is moles of solute over liters of the solution. Okay. And so what is molarity of a solution that has 45 grams of NaOH dissolved in enough water to make this volume of solution? So for A, we need to change our 45 grams of NaOH into moles. We can use molar mass as a conversion. Let's see, sodium. So it's about 40 point. It's 40. Let's call it 40 grams of NaOH, right? 23.17, 40. Okay, this will get us a number of moles. So about 1.125 moles of NaOH. And now the volume has to be in liters. So we take this 599 milliliters and move the decimal point to get 0.599 liters of the solution. Divide our moles by 0.599 to get 1.88 molar for the concentration. Okay, we continue on in B. To make 3.6 liters of a 6.4 molar solution of KOH, how many grams of solid KOH would have to would have to dissociate in the water? Well, we can set up, we have 6.4 molar equals X moles over 3.6 liters. So at this point, we need to solve for the missing moles, and then we can use molar mass to find the grams. So X equals 6.4 times 3.6, 23.04 moles. This is KOH. 1 mole of KOH has, see, 39.1 plus 17.01, so 56.11 grams. A really big number here. We should see this many grams of KOH. Okay. All right, let's go on to C. Molarity of a solution that has 35 grams of KCl dissolved in enough water to make 6.5 liters of solution. So for molarity, we need to find moles. So we'll go with 35 grams of KCl, just like up in part A. And we have 74.55 grams of KCl per 1 mole. Do the arithmetic, we should get 0.469483568, just kind of an intermediate response here. That many moles divided by our volume, which in this case gives 6.5 liters. This gives us a result of 0.072 molar. Any questions up to this point?
I don't understand
B?
Yeah, okay, so you multiply the 6.4 and 3.6.
Yes.
And then you get 23.04.
Yes. And that was moles, and then I multiplied the moles by the molar mass to find the grams of that substance we need.
So you found 23.04 moles. When you multiply those together, you find the mole
Correct.
of the solution.
Yes.
And then you do the moles by the grams. And you're looking for grams.
I think so. Yeah, how many grams of solid KOH would you use? Yep. All right, let's go on to dilutions. I will tell you, while I'm thinking about it right now, is I did put a percent mass by volume and a percent volume by volume concentration problems on the test. They're not on the review, but we did just go over them on the quiz. And so there'll be one of each of those on the test. Okay. All right, dilutions. When we look at dilutions, we look at an equation something like this. M1V1 equals M2 V2. Typically, our M1V1 is what we initially start with. So M1 should be high, while M2 should be low because we're diluting the concentration. We're making it smaller. And then as a result, we typically take a small amount of volume of that high concentration and dilute it to a larger volume. Okay. As a result, when you take molarity times volume, what unit do you end up with? So molarity times volume, you would get moles. So when you do a dilution problem, this says that the moles before the dilution end up being the same as the moles after, because effectively you are not changing the quantity of the substance there or the number of particles. You're just changing how much of it per volume, in a sense. So it's the same quantity of particles, you're just changing the volume, and so then we have a different concentration. So in A, so I'll move this back a little bit. So in A we have, if you want to make a solution, you want to make 5,600 milliliters of a 1.5 HCl solution, how many liters of 6 molar HCl are needed? 6 molar is bigger, So that's M1, and the corresponding volume with it is V1. And then 1.5 is M2. The corresponding volume with it is V2. So we can set up, we're trying to find V1. So we have our equation. You guys know that I like to manipulate my equation first and then solve. So this shows that V1 is M2 times V2 over M1. And then plug in the values that you're given. M2 is 1.5 molar. V2 is 5,600 milliliters. And M1 is 6 molar. Now in this process, the molars cancel, leaving us with the volume unit of milliliters for our final result, which is fine. In dilution problems, it doesn't matter if you do milliliters or liters, unless one, they specify it. And then as a caveat, if you're doing volume, or you have V1 and you have V2, just make sure that you're using the same unit for both. Okay, don't screw anything up that way. So 1.5 times 5,600 divided by 6. V1 would be 1,400 milliliters is how much we need to use of that initial concentration. Okay. In part B, molarity of a base if 2 liters of 12 molar base are diluted to volume of 13. Well, we have a small volume of something in high concentration, and then we are diluting the concentration to a larger volume. So M1 is 12 molar, V1 is 2 liters, V2 is 13 liters, and M2, we have no idea. So M1 times V1 equals M2 times V2. Manipulate the equation so that we solve for M2. And we have 12 molar times 2 liters divided by 13 liters equals 1.85 molar for that missing concentration. Okay, we'll finish up class here looking at part C. Recall that titrations, which are on here, won't be on the test. We'll focus on that in lab again Thursday and with the lab practical next week. So let's take a quick look at part C, which I'll flip the page to. All right, so part C, 2 liters of a 0.85 concentration, calculate the amount of 8 molar needed. M1 is 8 molar, V1 we don't know, M2 is 0.85, V2 is 2 liters. So we have our equation. We want to find V1. So we have 0.85 molar times 2 liters divided by 8 molar. .21 liters. Now, real quick as you go, that would tell us how much of that initial concentration we need, but do be prepared to find how much water you would need as well. Okay, I'll put it in here as you go. Volume of the water to make the solution is your final volume minus your initial. So if our final volume is 2 liters minus our initial of 0.21, then we have a resulting volume of 1.79 liters of water that we would add to this 0.21 liters of initial solution. That's it for today. Good luck preparing. We'll see you tomorrow.